Good morning. One of my discussion for today is all about algorithm logic unit, floating point conversions, numerical. Learning objectives. At the end of this video, the learners will be able to identify the different types of floating points, understand the concept of normalizations, evaluate the process on how to convert numerical numbers, perform the process on how to convert numerical numbers. Floating point. What can be represented in n bits, assigned and 2s components? What about a very large numbers? A very small numbers, a fractional values, mixed numbers, irrational numbers. The location of the fractional point radix can be moved from one location to another according to the precisions. That's where our name came from. It takes a general format as exponent, zero, fractions. That is all about a floating points. In a mathematics, radix point refers to the symbol used in a numerical representations to separate the integral part of the number. To the right of the radix between the baseline and the top numerals, in a base 10, the radix point is more commonly called the decimal point. Floating point representations. Numbers too large for standard integer representations or that have a fractional component are usually represented in the scientific notations, a form used commonly by scientists and engineers. Example, 4.25 by 10 raised to the 1 and 10 negative 3, or negative 3.35 times 3 negative 1.42 times base to the 10. Normalizations is the act of shifting the fractional part in order to make the left bit of the fractional point is 1. During the shift, the exponent is incremented. Normalized numbers are the numbers that have their MSB1 is in most left bit of the fractional part. The normalized numbers are the opposite of the normalized numbers. Example, the MSB1 is not in the most left bit of the fractional part. Operations. Some operations require that the exponent field is the same for all operands, like addition. In this case, one of the operands should be the normalized. Importance. The normalized number have important use in some operations and numbers. Assume the minimum exponent is negative 98 and the number of digits is 3 and to perform the operation. X minus y, where x is equal to 6.87 times 10 to the negative 97 and y is equal to 6.81 times 10 to the negative 97. The result of these operations is 0.06 times 10 to the negative 97. If this number is normalized in this math, it will be 6.00 times 10 to the negative 99, which is too small to represented as a normalized number, and so it is normalized to 0. But if the result is not normalized, we will get the correct result. Gradual underflow. One of the advantages of the normalized number is a gradual underflow. This came from the fact that the normalized numbers can represent a minimum number is 1.0 times 2 minutes. All the numbers smaller than that are rounded to 0, which means there are no numbers between 1.0 times 2 minutes and 0. The denormalized number expands the range and gives gradual underflow through the divisions of the range between 1.0 times 2 minutes to 0 with the same steps as the normalized number. Normalized floating point numbers. We are most interested in the normalized floating point numbers, a format which includes sign, significand, integer power of the radix. Examples of normalized floating point numbers. positive 1.23456789 times 10 to the 1, and negative 9.987654321 times 10 to the 12, and positive 5.0 times 10 to 0. That is the example of normalized, while on the other hand, negative 11.3 times 103 and positive 0.0002 times 107 and positive 4.0 times 10 and a half. These are not the example of a normalized number. To give you an example of conversion from binary to decimal, 1.00101 base to the 2 is equal to 1 times 2 to the 0 plus 0 times 2 to the negative 1 plus 0 times 2 to the negative 2 plus 1 times 2 to the negative 3 plus 0 times 2 to the negative 4 plus 1 times 2 to the negative 5 is equal to 1 plus 0 over 2 plus 0 over 4 plus 1 over 8 plus 0 over 16 plus 1 over 3 is equal to 1 plus 0.125 plus 0.03125 is equal to 156.25. That is the result of converting binary to decimal numbers. We can use another form like 37 divide 32 is equal to 1.5625. Another example of converting from decimal to binary. Let's start with 3.4625 times base to the 10 exponent 1 is equal to 34.625. Let's deal separately with the 34 since we are going to move the decimal point from left to right once. The equivalent of 34 to the binary is 1000010 base to the 2. Now, since we separately convert the decimal number to a binary, the 0.625, we are going to convert it into a binary. 2 times 0.625 is equal to 1.25, since we are going to get the whole number, which is the 1. 2 times 0.25 is equal to 0.5. Get the 0. 2 times 0.50 is equal to 1.00. Now, to write all of the answer, let's write them left to right in order to get the conversions of decimal to a binary, which is 34.625 base to the 10 is equal to 100,010.101 base to the 2. Another example of converting a decimal to a binary. 1.23125 times 10 to 1 is equal to 12.3125. Same with the previous example, we're going to move the decimal point from left to right once. We're going to get the equivalent of 12 to the binary. So 1100 base to the 2 is the equivalent of the decimal to a binary. Now we're going to compute the 0.3125 as to get the binary. 2 times 0.3125 is equal to 0.625, and 2 times 0.625 is equal to 1.25, and 2 times 0.25 is equal to 0.50, and 2 times 0.50 is equal to 1.0. The result of this, 12.3125 base to the 10, the equivalent number to a binary is 1100.0101 base to the 2. Normalizing a floating point data. Floating point data is normalized so that the significand is always 1. 10001.101 base to the 2 is equal to 1.000101 times base to the 2. To get the exponent 5, we are going to move the decimal point from right to left 5 times. 1100.0101 base to the 2 is equal to 1.1000101 times 2 to the third Same example with the previous. Since the most significant bit is always 1, we can assume that it is implied and that we do not actually have to represent it. Biased exponent. Short floating point numbers uses 8 bits for the exponents, which we want to range from negative 128 to positive 125. A biased exponent uses some value other than 0 as the baseline, which must be subtracted to get the actual exponent value. Here is the example in the short floating point numbers. Exponent of 135 minus 127 is equal to 2 to the negative 8, and exponent of 120 minus 127 is equal to 2 to the negative 7. Representing a floating point values in a memory. There are 3 standard formats for representing floating point numbers: a 32 bits format, a single precisions, and a 64 bits format, double precisions, and 80 bits format, extended precisions. A single precision with 32 bits, float and C. A sign is equal to 1, exponent is equal to 8, 23 is the mantessa or the fractions. Exponent exists a 127, a binary integer. A mantessa or a significant sign plus the magnitude normalized binary significant with a hidden 1 bits. Actual exponent is negative 127. X is equal to negative 1 as a sign bits and exponent of negative 127, and the mantessa is 1. Magnitude of a number that can be represented is in the range 2 negative 126, mantessa is 1, and 2 127, 2 minus 2 to 23, which is approximately 1.8 times 10 to the negative 38 to 3.40 times 10 to 38. Here is the example of converting a binary to a decimal floating point. What is a single precision hex number for the signed decimal numbers of negative 3.421875? Okay, we're going to follow this step by converting a binary or separating 3.421875. 0.000011 is the equivalent of 3 to binary, and 0.421875 is the equivalent is 0.011011. We're going to normalize to move a radix to most significant one. In this case, 1 place left. This is the step number 2. 0.10111011. We move 1 place from right to left. Number 3, we're going to calculate the exponent. Since 127 plus 1 is equal to 128. 128, we're going to convert the bias exponent to a binary, which is the step number 4. So 128, the equivalent is 1000000. Now, in number 5 steps, we're going to get the single precisions, which is 0.10001011000000. Double precision floating point numbers. A double precision, which is in the 64 bits, sign 1, exponent 11, mantessa is 52. Exponent exists of 1023, a binary integer. A mantessa or significant sign plus the magnitude normalized, a binary significant with a hidden 1 bit. Actual exponent is negative 1023, which is the bias. X is equal to negative 1, which is the sign, and exponent of 1023, and the mantessa is 1. Magnitude for numbers that can be represented is in the range of 2 to negative 1022, mantessa is 1, or the 2 positive of 1025, 2 minus 2 to the 52, which is approximately 2.2 times 10 to the negative 308, or 1.8 times 10 to positive 308. The triple E754 standard also supports extended a single precisions more than a 32 bits and extended double precisions for more than a 64 bits. The special values for the exponent and mantessa are used to indicate other values like zeros and infinity. This is the other example of decimal floating point. What is the double precision hex number that correspond to the signed decimal numbers of positive 3.4219? Same procedure that we used in the previous example. First, we're going to convert the binary of positive 3.4219, which is the 0.00011.011.011. Second step, we're going to normalize the binary. Of course, we move radix to most significant one in this case. Third step, we're going to get or calculate the double precisions of the exponent of 1023 plus 1 is equal to 1024. Then 1024, we're going to convert it from a binary that is the step number 4. Then we're going to get the single precisions of 1024, that is the fifth steps. Another example, what is the decimal double precision floating point number that corresponds to the hex number of 403140000? So we can use the equations x is equal to -1 times 2 exponent to -1023 times 1 the mantessa. Of course, the same procedures, we are going to convert the 403140000 to a binary. Number 2, remove the sign bits. And number 3, remove the bias to get the equivalent form. And number 4, insert and imply 1 and the normalized shift radix to the right 4 places. Special cases, the normalized numbers. A non-zero floating point numbers that has the following properties. Its exponent has reserved value, usually the format minimum. X explicit or implicit leading significant bit is 0. If the exponent is all zeros, but the fraction is a non-zero, else it will be interpreted as 0. Then, the value is the normalized number, which does not have an assumed leading 1 before the binary point. Here is the step on how to convert a floating point number as decimal that involve the following steps. Number 1, we are going to process the decimal number and a binary parts number and convert them into a binary format. Number 2, normalize the binary number by moving the decimal point to the leftmost part positions. Number 3, calculate the bias exponent. And number 4, convert the bias exponent into a binary. And number 5, substitute the required format in a single precision or in a double precision or an extended precision. Let us convert the decimal number of 263.3 into a binary numbers. In this case, let us follow the steps in converting a decimal number to a binary. First, separate the process, the decimal number in the binary parts, and convert them into a binary format. So we're going to convert 263 into a binary form. It shows the result. And we're going also to convert 0.3 into a binary, and it shows the result also. Number 2, normalize the binary numbers by moving the decimal point the left part positions. So the result of 263.3 in separating a binary is 100000111 0.0100110011. Now we have to normalize the binary by moving the left, by moving to the from right to left the decimal point, and it shows the result. Number 3. Calculate the bias exponent. The bias exponent is 127 plus 8, since the exponent is 8, is equal to 135. In this case, we will add the 127 to the exponent, which is 8. The result is 135. Now the 135, we will convert this into a binary. That is the step number 4. And number 5, substitute the required format of single precision, which is 1 sign bit is equal to 0. 8 bits is equal to 1000111. That is the equivalent of decimal number into a binary number of 135. The fraction of the order Mantessa is 00001110100110011. Combine all the sign bits plus the 8 bits plus the 23 fractions. That will be the result is 010000110011101011001110. In this case, we will divide it into 4 to get the whole conversions of 263.3 into a binary. That is the example in a single precision. So I hope you learn from this video. So that's all for today, and have a nice day. So I am Redentor.